Okay, I want to quickly go over number 3 here, just to review our position versus time graph stuff. Okay, so it's a displacement or position versus time graph. Okay, we want to calculate the displacement from 0 seconds to 4 seconds. Now, anyone remember how we calculate displacement? Right, final position minus initial position. Okay, the initial position is going to be at time 0 seconds. The final position is at time 4 seconds. So, at time 0 seconds, my position is 0. Okay, my final position at time 4 seconds is -4. Alright, well, that would mean my displacement is -4. That was pretty easy. Okay, alright, the total distance traveled. So anytime they say total, all right, they're looking for the whole trip here. So we already figured out what this part of the trip was. It was 4 meters. What is it doing here? It stopped, right, because it stayed at -4 meters. Its position didn't change. Okay, and then from here it goes from -4 to +6, which is 10 meters. All right, so the total distance traveled here is 14 meters. Remember, it's scalar. Distance is scalar, so it doesn't matter whether it went forward or backward. Okay, the average speed over the whole trip. Well, I just calculated one of the things I need to do that. Total distance. How long is the trip? 6 seconds. All right, so 14 meters. Okay, total distance over total time, 6 seconds. All right, that should give us 2.3 meters per second. Okay. And then average velocity over the whole trip. What do I need for that? What 2 things do I need for average velocity? Andres? Right, total displacement and total time. So, initial position, still 0. Final position, +6. All right, so I've got +6. Okay, divided by the total time, 6 seconds. All right, well, that gives us +1 meters per second. Okay, why does it have to be positive? Is velocity a vector quantity? Okay, were there negatives on the graph? Then I need to distinguish. All right. Okay, questions on number 3. Okay, how many people are past, let's say, question 6? Anybody? All right. Okay, keep going on that. I imagine we're probably going to be done fairly soon here. Okay, are there any ones right now you have questions on? Okay, I'm going to give you a few more minutes before I talk about the next thing we're going to do here. All right, so for number 5 here, guys, so it's a velocity versus time graph. First thing is total displacement over the whole trip. Okay, so what I've got to figure out is how am I going to get displacement if I have velocity on the y-axis and time on the x-axis? Well, if I want to solve for displacement, displacement's supposed to be v times t. Okay, now that's easy for a spot that's like this one here, okay, where it's traveling at a constant speed, and here where it's traveling at a constant speed. Actually, we'll say it starts at 15. Okay, starts at a constant. For those, it's easy. Then it's going to be whatever the velocity was times the time. Okay, so this ends up being -40 because it's -8 times 5. Okay, and this one here ends up being +40 because it's +8 times 5. Now, just looking at the shape of this graph, I should be able to just kind of quickly do this one in my head. It's exactly the same shape above the line and below the line, so they would cancel each other out. But I want to mathematically prove that anyway. Okay? Now, in this part, the velocity is changing. It goes from -8 to 0. All right? So what's the average between 8 and 0? 4. I can still use this as long as I put in that this is the average velocity, which would be, okay, VF plus VI over 2. Well, VF is 0 and VI is -8. Divided by 2 is -4. All right, so I plug that in, multiply it by 5 seconds, and I get that this is -20. Same thing with this one. Okay, my average velocity is +4. In other words, base times height over 2. And that's what I did here, right? Was the base times the height, this part here, divided by 2. Everyone follow me on that one? Okay, so I got 4 times 2, so this one here is positive 20, which is why the total displacement comes out to 0 meters. Okay, average acceleration between 5 and 15 seconds. All right, so it's accelerating, and the units for acceleration, or the formula we looked at the other day, and you're going to look at it more tomorrow, okay, VF minus VI over T is a formula for acceleration. Okay, that means that's essentially rise over run for any linear line on the graph. So between 5 seconds and 15 seconds, okay, if I want to find the slope of that line, I'm going to go positive 8 minus negative 8, right, over 10 seconds. So I'm going to have 16 over 10, which is positive 1.6 meters per second squared. All right, it's the slope of that line. All right, and then average speed over the whole trip. Okay, well, I did all this figuring here with the areas here, so I'll just write them back on. This one was 40, this one was 20, this one was 20, this one was 40. Okay, so I've got 60 plus 60 is 120 meters. All right, because remember, distance is scalar. It doesn't matter whether I was going backwards or forwards. Okay, and I'm going to divide that by the total time. Okay, which is 20 seconds. Well, 120 over 20 is 6 meters per second. And that's, sorry, I don't need positive on there, okay, because it's speed and it's scalar. Everyone all right with that one? Okay. How are we doing on number 6? How many people have done number 6? Okay, do we need to go over number 6? We're good? Okay. Oh, you want to go over it? Okay. All right, so this one's a little tougher because the grid lines didn't show up on the graph. Okay, it says calculate the acceleration between A and B. All right, well, acceleration, like we said, is VF minus VI over T, or the slope of the line. Okay, so we've got 20 minus 0 over 2 seconds. Okay, so 20 minus 0 over 2 should be 10 meters per second squared. All right, the displacement between A and E. All right, so I've got a velocity versus time graph. I've got, okay, this formula here that I want to use to calculate displacement. All right, now average velocity is going to be base times height, or base times height over 2, okay, for all of these things here. So for this one here, our base is 2, our height is 20, so 2 times 20 is 40, over 2 is 20. Okay, this one here, okay, is 2 seconds long at 20, so that's going to be 40. And then I'm going to have, sorry, I only need to go to E, don't I? All right, so I would say I'm going to do this a little bit differently since I only have to go to E. Okay, I'm going to calculate the area of all these other shapes. So I've got this triangle here, okay, and it's going to be 1 second wide by 20 high, so that's going to make its area 10. Okay, I'm going to have this one under here that's 20 high by 1 second, so it's going to be 20. I've got this one here that's 3 wide by 40 high, which is 120. Okay, so now I've got all the displacements during each section. Okay, now I can add them up and I'll have the total displacement between A and E. So 60, 80, 90, 210, right? Yep, 210 meters. Everyone all right with that? Okay, acceleration between F and G. That would be a 1-mark question. What's the acceleration between F and G? 0. Because it's not changing velocity. The line is flat. It stayed at 20 meters per second for that whole second there. All right, average velocity between A and F. All right, well, I've got the total displacement to E. I only have to do a couple more calculations to get the total displacement to F, and then I can do, okay, the total displacement over total time thing. All right, so for here, I've got 2 on the bottom by 20 high, so that's going to be 20. Okay, and this one here will be 40. So I'm going to add another 60 to that 210. So that's 270 over 10 seconds. All right, and that should give us 27 meters per second, and that's got to be positive. Okay, and then total distance traveled. Well, we'll just keep adding on here. We just got to keep calculating our little areas here. Okay, so that one will be another 10. Sorry, those will be 20. Okay, and this one here is 10 high by 1 wide, so it's 5. Well, what I would say is show your work. Like I would say show it on the graph like this, or show me your base times height calculations or something like that when you're doing a question like this. Because if I ever asked you to do that many calculations, it would be like a 6 or a 7 mark question. So, you know, I'd give you a mark for this area, that area, et cetera, et cetera. If you made one mistake, you're likely to lose maybe 1 mark, maybe 2, okay, depending on how many little mistakes you made. So that's a case where showing your work is a really good idea. All right, on a 6 mark question, if all you write down is the answer and it's wrong, you get 0, even though you probably knew 5 out of 6. All right, show me that you know 5 out of 6. All right. Okay, any other questions on 6? All right. All right, I'll give you a few more minutes here before we go over some others. Okay, guys, just want to quickly talk about question number 8 here with the position versus time graph that's all curved. All right, we talked about how you find instantaneous velocity from a curve, and that is that you draw a tangent line, because the tangent line you can calculate the slope of. All right, the idea here is that a curve is made up of an infinitely large number of infinitely small straight lines. If we can calculate the slope of any one of those straight lines, we know how fast the object was going at that point in time. All right, so for the first one here, it says calculate the instantaneous velocity at time 2 seconds. So you take your straight edge ruler, whatever you're using, okay, and you draw a tangent line that touches the curve at time 2 seconds. Okay, something like that. Okay, and then we calculate its slope. All right, so for me here, I'm going to use, I'm probably going to have to do a little bit of estimation here because I only got one good grid intersection. Well, maybe this one here. I'll use this one here. All right, so I'm going to use this point here as my one grid intersection, and I'm going to use this one over here as my other. Okay, I want to calculate the slope. That's going to be y minus b over x equals m. Okay, my y value for this point is 10. Okay, my y-intercept is 5. Okay, and x is 2 seconds. All right, so I'm going to have 5 over 2, okay, which is going to give me 2.5 meters per second. Now the answer I got the first time I did this was 3, okay, and I just helped someone do this and they got 3.75. Right? Obviously there's a bit of leeway here when you have to draw a tangent line that touches a curve. We could all get considerably different slopes of those best fit lines, especially when they're this short. Okay, so obviously there would be quite a bit of leeway in there, but that's how we would go about doing that type of a question, right? And it's the same everywhere on the graph. Okay, for example, if I was looking at let's say time 20 seconds, let's say, okay, I would do the same thing. Right, this time my curve is probably gonna have to go on the inside. Well, that is nowhere close. Okay, so I'm gonna make that a little bit steeper. Yeah, that's a little bit better. Okay, so now I can calculate the slope of that line and see how close I get to the first answer I had. I can't use y equals mx plus b here. Why? Well, it doesn't need to cross the origin, but I have no idea where the y-intercept is going to be because it's way up here somewhere where I don't have any graph. Okay, can I still use rise over run? That's why we have 2 ways to do things. Okay, this time I'm going to use rise over run, so I'm going to find 2 points that are good grid intersections. I'm going to say that down here, right on the x-axis, is going to be a decent grid intersection, and probably right here would be my other one. All right, so at 25 here, and then this one goes down to 14. All right, so m equals, and we're going to have y2, which is 0. Okay, because it's down here, minus y1, which is 15. All right, and divided by the total time, which is going to be, so x2 is 23 minus 14. All right, so I've got 15 over 9. Okay, and That actually looks like it might be half close. Yeah. Who's the man? Okay. Yeah. All right. Okay. Is everyone with me there? All right. How are we doing? Are we getting pretty close to done? How many people are done? All right. Good. Okay. So guys, if you get to this sheet, that's great. I would say that this is probably a good thing to keep around. If you don't do it right away, that's probably all right. But like when you're studying for your unit exam, okay, it'll be kind of useful. I'll make sure that the key gets up on the website so you can look up the answers and know if you're doing them right or not. But essentially, it's the same thing we've been doing all the way along. Thursday's quiz will also be very much like this, okay? And maybe it'll have a position versus time and a velocity versus time graph. You'll find that out on Wednesday, okay? So just be ready for that. Obviously, you won't have a quiz tomorrow because I'm not here. All right, so you won't get a quiz tomorrow, but you will get one on Thursday.